Okay, so now we know what expectation is. Let's talk about some rules for expectation that are going to make it mathematically convenient for us to work with these quantities. The first rule, which is very important, is that expectation is linear. What we mean by linear is if you're not, doing a lot of math, there's nothing about this that suggests a line to you. But let me first explain what it is, and then maybe we can talk about what is linear about this, or why we say linearity is a thing. So here we have the population average, and we're asking about the population average of this measurement, which is a times x plus b times y. So this is a derived measurement. So let's say you measure x and you measure y. And now I'm asking, what is the average if I make a new measurement? Like if you imagine your population data set, you have columns x and y, and you do a mutate in your population data to get a new column z. And the value of z is ax plus b times y. So whatever is an x, you multiply it by some number a. So let's say a is like 2 and b is 1. And then so here it would be like 2 times x plus y. That's what's going to be in the z column. So this is a new derived measurement. And what this rule says is that the population mean of that new derived measurement is going to be exactly the population mean of x times whatever a was, plus the population mean of b times whatever b was. So in other words, this expectation, you can kind of bring it inside of the sum and of the constants. And what I'm writing down here is it's just what I said, like, imagine doing a mutate where for each person their value of z is going to be equal to whatever the value of x they had plus the value of y times these constants. Okay. So the reason this is called linear is if you have a function that looks like this, so this is g of z, for numbers z that are like single dimensional, we know that the equation for such a thing is just m times z. So this is the slope of the line. And what this means is that if you put into g ax plus by, that's just m times ax plus by, which is the same as m ax plus m by, which is the same as, I'm just going to switch the order of these two, a times mx plus b times my, which you will recognize as a g of x plus b g of y. So this is the property that defines linearity. And it seems really obvious and kind of stupid for kind of functions, one-dimensional functions of a single-dimensional variable. But this property, actually, you can use it more generally. So here, expectation is a function that you give me a random variable and I give you back a number. So it's much more complicated than this, but it still obeys this property. And so we say that expectation is linear because it obeys this property. And you see this again and again. In math, there's a lot of different operators and functions that are linear, even though you can't really think of them as like a line per se, or as having a graph, because they're mapping not between numbers to numbers, but between random variables and other more complicated objects. So this is just why is it called linear? Okay. What's more important is knowing that you can do this, that you can pass the expectation through sums and putting it in front of constants. So why? Why is it that this is true? And you can derive this from starting at the definition in terms of a population average. So if I have a random variable z, I can write the expectation of z as this population average value of z. And now all I need to do is replace z with what I defined it to be here, right? And now I can break up the sum as a sum over first this part, and then because here I'm just adding x for person 1, y plus for person 1 plus x for person 2, y for person 2. So instead of adding it in that order, I could just add up all the x's for everyone, and then add up all the y's for everyone. So I've just split the sum like that. And then this constant comes in front of both of them. And since this is a constant, I can pull that out too. So that comes out. And now you'll recognize that this is precisely the definition. This is the population average of x, and this is the population average of y. And so we're done. And we have proven what we had to show. And you can also prove this from the more the definition of the that uses the densities, but it's harder, more mathematically tricky to verify. And this is the thing that gives you the right intuition. Okay, so let's play around with this a little bit. So let's imagine that x is a normal distribution with mean of 1 and variance of 1. So first thing is, let's sketch the density. So here's 0, this is 1. So if it has the mean 1, it's going to look like this. Okay. Question is, what is the expected value of a times x? Well, based on what we literally just did, we know we can take the constant out, and this here is this, right? So that's just a. So we know that the expected value of this the scaled version of this random variable is a. The question is, what do you think the density of ax looks like? So what do I mean the density of ax? Well, this is just another random variable z, right? Again, think of your population data. I just did a mutate. I have x. I did a mutate to get a new column z. I had a histogram for x, and now my question is, what does the histogram for z look like? All right. So just think about that. The right way to think about it is like this. So let's take a whole bunch of people who are here. So all these people. So they have values of x that are near 1. Where are they all going to go in terms of a times x, right? So all these people, they had a value of 1 for x, so their value of z will be a. So let's say a is out here, okay? So all of these guys are going to go there. And there's the same number of them. So let's say there's like 100 people here, right, in this little chunk. So there's going to be those same 100 people, had value 1 for z, for x, must have value a for z. So all those people are there. And let's maybe draw it a little more cleanly. So I'm just kind of going to take this little stack. Take this little stack of people. And then I'm going to put them all over there at the value of a. Okay. Now, let's look at the people who are next to them. So let's say at 2. Okay. This little stack of people. They're going to go to 2 times a. So if this is a, 2 times a is like over here, right? So this group of people, the value of z is going to be here. There's the same number of them. Let's look at the people at 1/2. It's kind of drawn badly, but like here. So this is 1/2. Where are they going? Well, their value will be 1/2 of a. So it's like here. So these guys are all moving over here. Okay. So you can play this game, and what you're going to see, and let me maybe put this in a different color, is that by multiplying by a, we have shifted this thing over, but we've also spread it out like that. Because these people who used to be kind of this far apart are now being scaled by, and so here we have 1/2 a, are being scaled by that distance from in a. So that's the intuition. And I'll leave this one to you. You can do this. Just do what I did here. Draw like, a million people from the standard normal distribution to get your population data frame. Population data frame, right? It's just a very large sample. Do the mutate to make a new variable z that's like, let's say 5 times that random normal that you had. and then make histograms of x and z, and you'll see it looks basically like this. And what you should notice is that the expected value of the yellow curve is exactly at a, right? But it's interesting because sometimes people assume, oh, if I'm multiplying it, maybe what's happening is that it's just being shifted over like this, because that would still have the expected value of a, but it's actually also scaling it. And we're going to see that when we talk about variance in a little bit as well. All right. Next problem is to create the following data generating process in R. And then we want to sample to approximate the expectations of x, y, and z and see how they're related. So what do we have here? It's some large number. Okay. So here's my population data frame. It's actually not a population. It's a very, very large sample, but close enough. And so let's calculate those expectations. We can do it like this. Mean of x, mean of y. You know what, actually? I think it has to be like this. Okay, so these are the expectations. So the I think maybe we can do just so you can see it. There we go. Cool. So this is the expected value of x. It's about -1/2. The expected value of y is 1/2, and the expected value of z is approximately 0. And this is what you should expect, because the way I've set this up, if you remember the table that we had of what are the expectations of random variables from standard distributions, the normal one's one of them. So we know just from looking at this that the mean of x is -1/2. Similarly for y, uniform distribution, the mean of this will be +1/2. So that's exactly what we have here. We've approximated those closely. Mean of z, since expectation is linear, I can just take the expected value of x and add it to the expected value of y. So -1/2 plus 1/2, 0. And that's also what we see here. And we can also look at some densities in histograms. So let's have a look at that just to check something out. Okay, good. Just do okay. Good enough. If you don't follow this, don't worry. This is not the purpose of the course. I was just trying to make plots that are kind of pretty here. But if you think this is kind of cute or interesting, or oh, how did he do that? Then of course, feel free to throw this into ChatGPT, Google these functions, learn a little bit more about how I've done this, and of course ask questions on ed or in office hours if you're curious. But you're not going to be evaluated based on this. Okay, so what are we doing here? We have a random variable x. X is a normal with mean minus 0.5 and standard deviation 1. So this is like your kind of standard bell curve, except it's shifted over, not at 0, it's at minus 0.5. And then y is a uniform random variable. So all the mass, this variable only people only have values between 0 and 1, but between 0 and 1, there's any value is equally likely. And then z, why does it look like this? And is this what you expected, or is it not what you expected? I think it's worthwhile to think about this and consider why z kind of looks like this and what's going on. So think of it this way. Imagine that y, instead of a uniform over 0, 1, imagine if y were just deterministically 1. It were always 1, no matter what. Or some number very close to 1, like 1.1, 0.9, something like that. Then would it make sense why, if you do x and then z is y plus x, anybody who had value minus 0.5, it would now be exactly 0.5. And anyone who had value of, let's say, minus 3 would now be 2, and so on and so forth. And so that would just shift this curve over in this direction here, which is kind of what we see is happening. But what you notice is that this is not actually shifted over so that the peak, which would be at 1 if, would be at 0.5 if we had shifted it over by a full unit, which is what would happen if y were 0 and then just 1 and then 0. It's not shifted over all that way. Why? Because some of these people are getting shifted over by the full 1 unit, but then some of them are being shifted over not at all, because some people have y equals 0. Some people have y equals 0.5. Some people have y equals 0.7. On average, the average value that y is taking is 0.5. So the kind of average shift over here is 0.5. So that's why this is being shifted over a bit. And it's also hard to see, but this distribution is also spreading out a little bit. And the reason is because of the spread here, because the people, if you, like, let's say you're sitting right here and the value for y that you get is 0, you're not going anywhere. Your value for z is going to be the same, right? But if your value for y was 1, like let's say you had a neighbor, somebody who is standing with you on the x-axis, but your value for y is 0 and their value for z is 1, now they're getting spread out from you. And so there's spread that's happening, which is going to increase the overall spread. And you can see that more clearly if we instead make it uniform from, let's say, 0 to 5. We're going to see a lot more spread happening because we're spreading out locally. And you see that that's exactly what happens here. So this is our value of x. And then this is my value of y, and then my value of z. So I'm shifting it over because these are all positive numbers, but I'm also spreading it. So that's not totally all related to expectation, but it's hopefully helpful in terms of thinking of transformations of random variables, adding and subtracting random variables, things like that, how that changes distributions. Okay, so besides linearity, there's other nice properties of expectation. So another common thing is often you want to take the expectation of some derived measurement, and sometimes that derived measurement is a linear function of x, like ax plus by or something like that. But sometimes it's a nonlinear thing. Like, what if you have a variable x, like blood pressure, right? And then you actually want to take what you want to know what the average value of the log of blood pressure is, or something like that. How can you compute that? Well, the intuition is the same, right? So it's just the population average of whatever this new variable is. So g of x, this could be like, log blood pressure. So, okay, you just ask person 1, what's their blood pressure, take the log of that. Add it to person 2, what's their blood pressure, take the log of that, so on and so forth, divide by n. And so by doing the same manipulations as before, you can show that in terms of the density function, it's the density of x, so this is blood pressure, But now it's not multiplied by the value of blood pressure, it's multiplied by whatever value this transformation takes. So the log of blood pressure or something like that. If this is confusing, I recommend you stop the video and go back to where we kind of derived how to go from here to here. So you're going to have that table, the population data set. The only difference that you're going to do is you're going to have another column now where instead of x, it's g of x. And if you just follow that through where you're taking the population average of g of x, you're going to see that this is what comes out. So that's a useful rule to know. Another kind of cute thing is that probabilities are actually expectations of particular transformations of random variables. Okay, so what do I mean by that? So here's a, let's say you have a random variable x. So this could be like height. Okay, it's an easy example, right? So if I take, there's this transformation is an indicator function that, remember, this says return the value 1 if x is in the set A, and 0 if x is not in that set A. So for example, we could say if A were, I said this were like between 5 feet and 6 feet. And so again, think of it in terms of a population data set. You can have people's height here, right? And then this could be, again, in feet, 5.5. You get NBA players in here, whatever. And then if you have the indicator of the set from 5 to 6 of x, that's just going to give you a 1 wherever this condition holds. So here, this is 0, 1, 0, so on. So this is the, again, population data. This is the transformation applied to this random variable. And I want to know, what's the average value of all these 1s and 0s? Well, by the thing that we just learned, all I need to do is take the density of x and multiply it by the derived value, which is this indicator of whether x is in A or not, and sum up over all the values that x can take. Well, if you look at this, remember this is just a shorthand, right, for like f of 0 times 0 plus f of 1 times 1 plus f of 2 times 2, and so on and so forth, okay? And the thing is that here, actually, instead of, here we have this transformation, right, which is going to be like g of 0, g of 1, g of 2, except in our case, the g of 0, 1, 2 is either going to be a 1 or a 0. So a lot of these are going to be zeros, okay? A lot of these guys are going to be zeros, and they just drop out altogether. And the other ones are 1s, right? So this one is like a 1, and this one's might be, the g is going to be a 1. And so what we're left with is just the sum of just the densities for the ones, I said it was this one, for the terms where g is equal to 1. So where is g 1? G is equal to 1 when x is in the set A, right? So when we're asking about heights between 5 and 6 feet. So we're adding up the value of the density just for the cases where little x is in the set A, which if you go back to the lecture where we talked about densities and how to compute probabilities from densities, this is exactly the probability that x is in the set A. And for continuous random variables, you get the same kind of thing. You just integrate over the set A of the density, and that's the probability. But it's the same thing, because this integral here is integral of 1 x f dx, and then integrating over this, if this integrand is 0, where it I'll draw it like this. So it's like you have this function. So here's f, and then you're multiplying it by the indicator of the set A. So here's the set A. So this thing is 1 when this function when we're inside of that set, and 0 otherwise. So this integrand in total is going to be the function that looks like this. 0 everywhere in here, and then it jumps up here, and then blah, 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 and then goes back down. And so we're asking about this area under the curve here, but all the area here and here is 0, right? So really we just need to integrate here. And that's what this is saying. So whichever way you want to understand it, you don't have to do the math. I'm just trying to get at the intuition. And this is just really a special case of this general rule here. But it's kind of interesting because it means that mathematically sometimes it's easier actually to work with statements like this than it is to work with statements like this. So you can often derive a lot of stuff about probability by working with expectation, or vice versa. They're kind of like mirrors of each other, like which came first, the chicken or the egg. You know, the way that I'm teaching it is like, okay, this is the egg and then we get chickens. But mathematically, you can start with chickens and get eggs.